Hello everyone, welcome to the post-contest discussion of the Codeforces Global Round 27. This is TLE Eliminators and I am Abhinav Kumar. Let's get started with the first problem. Okay, so in the first problem, we're given that there are n rows and m people. Let the position in the rth row and the cth column be denoted by r, c. Number each person starting from 1 in row measure order, that is the person numbered r minus 1 into m plus c is initially at r, c. The person at rc decides to leave to fill the gap. Let the person who left be numbered I. Each number j greater than I will move to the position where the person number j minus 1 is initially at. The following diagram illustrated. Okay, so basically what it means is that we are given N, M, R, and C, four things. N and M denotes that you can understand there are N rows of M people. Okay, so like if N is 2 and M is 3, like this you can see we have like 6 people here, 2 rows of 3 people each. Okay, so this is N, this is M. Okay, after that, now we have 6 people. Now what happens? R comma C denotes the coordinate. So starting from here 1, 2 and here 1, 2, 3. Okay, so R is the row number, C is the column number. Okay, so if R and C is given, like in this test case here, this person is denoted by 1 comma 2. Okay, the coordinate here would be 1 comma 2. Okay, so if this person leaves, what would happen? Okay, the persons are numbered like this in row measure order. So this person is numbered 1, this person is numbered 2, this person is numbered 3, then 4, 5, 6. Okay, like this the persons are numbered. Now if this person leaves, what would happen? All the j greater than I. Okay, so all the person numbered greater than him would move one place to the would move to the position of the person j minus I. Okay, so person number 3 would move to position of person number 2. So he would move here. Person number 4 would move to the position of person number 3. So person number 4 moves here. Person number 5 moves to the position of person number 4. So he moves here. Person number 6 moves to the position of person number 5. So this person would move here. Okay, so after the movement, this is the resultant. And now we need to find, okay, so every person has some movement. We need to find the sum of Manhattan distances of each person's movement. Okay, so Manhattan distance is defined as, like, if you want to calculate the Manhattan, if this person is moving from here to here, Manhattan distance is just the difference in the x coordinate plus the difference in the y coordinate. Okay, r naught minus r1 plus c naught minus. So difference in x coordinate plus, so if person moves here, so this plus this much would be the Manhattan distance of these two positions. I hope you understand. So we need to find the sum of Manhattan distances for all the person. Okay, so let's go there and understand it more clearly. Okay, so if we take the first test case, what is happening here is, okay, we are given N, M, R, and C. Okay, so we have, you can understand, a grid of 2 cross 3. Okay, so there are people in there are 2 cross 3, 6 people here. Okay, so the rows are numbered 1 and 2, columns are numbered 1, 2, 3. Okay, so and the people are numbered in row measure order. So 1, 2, 3, 4, 5, 6. This is the numbering of the people. So r comma c is 1 comma 2. It means it points to this guy. So when this guy moves from here, what happens? Okay, so this guy gets removed. Now he would move here. This person would move here. This person would move here. This person would move here. Now, what is the sum of Manhattan distances of all the movements? Okay, so when we see, like, when person 3 moves to position 2, person 3 moves here, the distance here, it would be, okay, this distance is just 1. Okay, difference in the x coordinate is 1 and difference in y coordinate is 0. Okay, so this Manhattan distance would be 1. Okay, so when 4 moves to 3, so when 4 moves to 3, the distance, okay, so when this position moves to this position, the difference, this coordinate is 2 comma 1. this coordinate is 1 comma 3. So difference in x coordinate is 1 minus 2. Okay, so this one distance, difference in y coordinate is 1 and 3. Okay, sorry, the x coordinate and y coordinate, whatever you want to call. So this coordinate is 1, this is 2. Okay, so 1 plus 2, total of 3 is the Manhattan distance from here to here. I hope you understand. Okay, how Manhattan distance is calculated from here to here. It is, you can say, this distance. Okay, so this distance would be 3. When 5 moves to 4, when 5 moves to 4, this distance would be 1. When 6 moves to 5, this distance would be 1. So the sum of these distances is equal to, here you can see, 6. So 6 is the answer for my first test case. Okay. I hope how it is calculated you understood. Now we need to just find this final value, and you can see this R and CM all are up to 10 to the power 6. Okay, so like we would try to derive some formula only and get it in order of 1, that would be best. Or we can go up till, like, it is 10 to the power 6, so we can go up till order of n or order of m. But if we are going to every cell, every movement, that would be n into m, so that won't be accepted if you are calculating for every basically cell. So you would have to derive some formula in order to pass. So basically what you need to do is, you have a grid, there is some position in this grid which is called, let's say, there is some position r comma c here. Okay, so this corresponds to the rth row, this corresponds to the cth column. Okay, now when this person moves, what would happen when this person moves? So for all the people in this row, they would move one to the left, one to the left, one to the left. For all the people in the rows below, okay, what would happen for the people in the row just below R, in row number R plus 1? Okay, the person just here, he would move to the end of the previous row here, and the remaining people would move one to the left, one to the left, one to the left. This is what is going to happen. So basically, I can say for all the, like, if you divide it, okay, so this first person from the R plus 2th row, and likewise the first person from the nth row, they are going to move this much distance to the end of here, and remaining all the people, all these people are going to move just plus 1 distance. So for all these people, except the front except the people in the first column, for all these people, we would add a plus 1 to our answer. For all these people also, we would add a plus 1 to our answer. Now for these people, how much are we going to add is, what is this distance? This is 1 and this is m. This would always be m. For these, the distance they move is m plus 1. Okay. How much this person moves? 1 here and m here to go to there. So m plus 1 is the movement for this person. He would move here. M plus 1 is the movement. Okay, so basically we can say that for all these people, we would have m plus 1 added for every person from r plus 1 to n. So how many people are there? It is n minus r, you can say. Okay, there are total n rows minus r. If you do, these are the count of the number of rows below r. Okay, so you can say it is n minus r multiplied by m plus 1. This much would be added due to these people. Now, what about these people? Okay, so all these people except the first column, okay, they would move just one place. Okay, so how many are there? So these many, n minus r number of rows, and this is m minus 1. Okay, because if you remove just the first person, so every row has m minus 1 people, m minus 1 people, m minus 1 people. So this value, I can say this would be n minus r multiplied by m minus 1. Okay, and plus I would add this much value also. all the person to the just right or in the same row. So how many are there? This is the cth column. This is the mth column. So these would be m minus c. This length would be m minus c. I hope you understand. If you remove the c from here, m minus c would be remaining. So for these people, the value we add is m minus c multiplied by 1. You can say all of them would just move by 1. Okay, so basically I can say my final answer is going to be the sum of all these parts, this plus this plus this. Okay, so my final answer is, if you add m minus c from here plus n minus r times here m plus 1, and these like we can take common and write n minus r into m plus 1 plus m minus 1, it is 2m. Okay, I think this would only be the formula, or if I'm not missing anything. Okay, so answer would be m minus c plus n minus r times 2m. Okay. Let me just check. N minus r times. Okay, sorry, it's coming to m minus 1. Just a second. Here we have m minus 1 people multiplied by n minus r. And here these movements are 1 plus, okay, sorry, it's m only, not m plus 1. This movement, if you see, 1 above, and here from 1 they are going up till m. So this whole movement is m minus 1 in this way and 1 in this way. Okay, sorry. So instead of m plus 1, it would be m only. Okay, like I hope you get it, that every person, he would move 1 above and m minus 1 steps to the right. Okay, he's already at 1. To move to m, he would move m minus 1 steps. So total of m steps for these people. Okay, so n minus r times m it would be. Okay, so overall it becomes n minus r times m plus m minus 1, 2m minus 1. Okay, so this is my final formula that we get. Okay, I hope this is clear to you. You had to just basically use a little bit of maths and calculate. This was very simple to calculate. I hope you did that. So this would be my final formula. You have to just write this formula in your code. So you can see, I just took the input n, m, r, and c. My final answer is n minus r times 2m minus 1, n minus r times 2m minus 1, plus m minus c. Okay, like, do you have any doubt? Wait, wait. Do you have any doubt? Okay, okay. If anybody has any doubt, you can ask.
सर वो फॉर्मूला फिर से एक बार बताइएगा सर, जो ड्राइव किए हैं, लाइक जो डिफरेंस था ना, m प्लस
Okay,
1 इंटू n माइनस r प्लस वाला।
okay. Like कौन सा पार्ट? ये 3 पार्ट्स में मैंने डिवाइड किया। जो इस
अब
पॉइंट
वो
के जस्ट राइट में, इस रो में, या m माइनस सी पीपल है जो एक एक लेफ्ट जाएंगे, तो m माइनस सी इंटू
ठीक
1
है।
हुआ। ठीक है।
हम्म
इस पार्ट में क्या था? ये सारे पीपल एक एक लेफ्ट में जाएंगे, और यहाँ कितने लोग हैं? n माइनस आर रोज, हर रो में m माइनस
हाँ
1
हाँ,
पीपल एक्सक्लूडिंग द फर्स्ट। सो n माइनस आर इंटू m माइनस 1।
ठीक है।
एंड ये सारे लोग क्या है, ये यहाँ से इस रो के एंड में जाएंगे। सो प्लस
हम्म
1 प्लस m माइनस 1। ओके, टोटल
प्लस
m का मूवमेंट है इनका, मैग्नेटिक डिस्टेंस
प्लस
फ्रॉम
नहीं।
हियर टू हियर।
हम्म,
सो
हाँ,
this difference in x coordinate is m minus 1, difference in y coordinate is 1. So 1 plus m minus 1 हर एक का मूवमेंट होगा, यानी m, और ये टोटल n minus r पीपल है, तो n minus r into m।
ठीक।
सो इन तीनों का सम अगर करेंगे तो ये आता है फाइनल। ओके, सो आई होप दिस problem is clear to everyone. If anybody has any doubt, you can ask now, or we'll move to the next problem now. Okay, you had to just derive this formula. So time complexity would be obviously order of 1 here, because you are not doing anything, just taking the input in order of 1 you are calculating. So time complexity is order of 1. Same for the space complexity, that would also be order of 1. Okay, so I think we can move to the next problem now. Okay, so problem B, we have you are given an positive integer n. Find the smallest integer whose decimal representation has length n and consists only of 3s and 6, such that it is divisible by both 33 and 66. If no such integer exists, print -1. Okay, so basically here you are given a n. What you need to find is, you need to find the smallest such integer whose decimal representation has length n. Basically, you need to find an n digit number, smallest n digit integer, so that it consists only of 3s and 6. Okay, the digits it has is only 3 and 6, no other digits is allowed, and that complete number is divisible by both 33 as well as 66. Okay, and if no such number exists, then print -1. Otherwise, you need to find the smallest such number. So if you take the example, if I take n equal to 1, so n equal to 1, it means I can only have one digit, and that digit can either be a 3 or a 6. Basically, so for n equal to 1, my only cases would be either 3 or 6. Now, neither 3 nor 6, they are divisible by 33 or 66. So for this, they both are not satisfying. So for 1, we would print -1. We don't have any such number which is satisfying our conditions. Okay. Now, if we look at length 2, okay, so for n equal to 2, using 3 and 6, what all two-digit numbers can we form? Okay, we can form 33, we can form 36, we can form 63, we can form 66. These are the only possibilities of two-digit numbers using 3 and 6. Among them, we need to find those numbers which are divisible by both 33 and 66. Now, 33 is divisible by 33, but not by 66. This is not divisible by any, not divisible by any. 66 is divisible by both. So this is fine. So we only have one number that satisfies it. So that would only be the smallest. So for 2, we print 66. Okay. Now for n equal to 3, what happens? For n equal to 3, we need to find a three-digit number consisting of only 3s and 6, so that it is divisible by both 33 and 66. Now, we can see from the test case, its output is -1. Like whatever combination you try, you can never form a number which is divisible by both 33 and 66. So for this test case, my answer was -1. For n equal to 4, if you look, the answer was 3366. This is such a number which is divisible by both 33 and 66. Okay, so I hope you understood the problem, and by looking at the test cases only, some answers also you got. So now let's try to find, in general case, what would our answer be. Okay, so the first thing that we need to notice here is we need to find a number which is divisible by both 33 and 66. Now, since you know what is 66, it is 33 into 2 only. So if any number is divisible by 66, it would definitely be divisible by 33. So basically the question is just to find that the number should be divisible by 66. Then only it would be divisible by both. So instead of in the question writing both 33 and 66, if you just write 36, the question remains the same. If you just write 66, the question remains the same. Okay. So you just need to find a n digit number consisting of 3s and 6, which is divisible by 66. Now, what all numbers are divisible by 66? So for small test cases 1, 2, 3, you know the answers from the given sample only. Now for large test cases, let's see if we can maybe find some pattern or something. Okay, so let's go here. So for n equal to 1, our answer was -1. For n equal to 2, our answer was 66. For n equal to 3, our answer was -1. For n equal to 4, our answer was, you can see, 3366. N equal to 5, our answer was 36366. n equal to 7, our answer was 3336366. Okay, so these answers we know from the given test cases only. Now, first I hope you understood the first three cases. Now for n equal to 4, let's understand why this is our answer. So, and for n equal to 4, you need to find a 4-digit number, the smallest 4-digit number such that it is divisible by 66. And we can use only 3 and 6. Okay, so if you need to find the smallest, we would try to use 3 more. Like initially, if we greedily use 3, that's better than using 6, and if we can get any uh, combination. So by value, the greater digit is more significant, obviously, so if we have a 3 here, then whatever we get, that would be smaller than if we start with 6. That obviously, so first we would try if using 3 we can get some number which is divisible by 66, then we would use 3 only. Okay, so we tried using a 3 here. Okay, then again we tried using a 3 here. Now for last 2 digit, if we just do 3 3 3 3, now if we try to check this, uh, it is not divisible by 66. Okay, so we need to, so the smallest one which is divisible by, after this the number that would come is 3336. This is also not divisible by 66. After this we get 3363. This is also not divisible. 3366, this was divisible. Okay, so for n equal to 4, I hope you understood that 6 was the smallest number. So let's now try to analyze and find for a general any n length digit. If you want to find, how can we find this? So first thing is, if you have n digits, okay, and we want to check that it should be divisible by 66. Now, what all numbers are divisible by 66? For the like tens and ones place, if you have like 33, 36, anything, they won't be divisible by 66. So like one thing is almost sure that in the last 2 digits, you would have to have 66 so that the final number is divisible. Like you may have some, maybe you may think that you may have some like 636 or something like those cases where the overall number is divisible by 66. But if you just try, then there would never be a case where you have some number and at the last 36 or 33, anything you can try, they won't be divisible by 66, because the remainder with anything 3 into 10 to the power anything mod 66, they like it won't be something to which if you add 36 or 33, they would become overall 0. So like by observation, you can notice that that in the last 2 digits we would surely have 66, but before that we would try to make 3333s so that we make the number smallest. Now if you look with 33, what all numbers are divisible? 33 is not divisible, but if it is placed towards this side, okay, so if you look 330, this divided by 66 is 5, so this is divisible. Now after that, if we multiply by 10 anything, so 330, it would always be divisible. So 33 with any digits, like any number of zeros, this would always be divisible by 66. So if you have 266 in the starting, then we can fill the remaining by 33. So 33, like if you are writing a number as 3366, this number is actually 3300 plus 66. This is also divisible, this is also divisible, so this overall number is divisible. If you write 333366, this can be broken down into 330000 plus 3300 plus 66. Okay, so this number is equal to this, where you can see that this is divisible, this is divisible, this is divisible. So overall number is also divisible. So whenever n is even, like you can see we have pairs of 3333 and at the end we have a 66. So for even case, we can say when n is even, we would have this kind of pattern, 3 3 3 3 3, and at the end we have 6 6. This would be our answer. Like, just by observing the test cases, you can see for even when n was 4, you had 3 3 6 6. Okay, when n was 2, you had just 6 6. For n equal to 6, your answer is going to be n equal to 6, your answer is going to be 3 3 3 3, then 6 6. So by looking at test cases, you can observe this, that for even you would have 3 3 3 3, so pairs of 3 3 3, and at the end the last pair would be 6 6. Now what about the odd case? If you look at n equal to 5, now for odd case you cannot have, if you try to, like, for n equal to 5, if you try for n equal to 5, like with the same theory for even case that you had, at the end you need 6 6. So before that, just place 3 3 3. But is this number divisible by 66? If you check, it is not divisible by 66, because you can break it down into this 33 can be broken down as 3300, 66 as 66. But this 3 into 10 to the power 4, this thing is not divisible by 66. Okay, 3 into 10 to the power anything, this number is never divisible by 66. Okay, so for odd case, when you have a single 3 left, it won't be divisible by 66, but you need to have pairs of 3s, so that is divisible by 66. So this thing won't be accepted for odd case. Now let's look what is my answer for n equal to 5. It is 3 6 3 6 6. Okay, so like by looking at this, and then n equal to 7, if you look, 3 3 6 3 6 6. So we can notice last 4 digits we are getting like 6 3 6 6. Okay, here also we were getting 6 3 6 6. So basically, okay, for n equal to 5, 1 2 3, for n equal to 7, my answer was triple three. Okay, 1 3 I missed here, triple three. Okay, so basically n equal to 5, we are getting 6 3 6 6. Here also we are getting 6 3 6 6. So if you look like 363, basically this 66, this is divisible by 66. Okay, you would break down this number into, so initially we would have pairs of 33 33, but for odd case where we were stuck is you have a single 3 left and then 66. So instead of a single 3, if you have three numbers which is divisible by 66, then you can solve this case. So if you take 633, okay, 363, if you take this number, so if you divide this 36366, okay, for n equal to 5, your answer was 36366. So if you divide this number into this part and this part, so 36300 plus 66, then this number is divisible by 66, this number is also divisible by 66. Okay, so if you look like, if you use a calculator and just try 363, this was not divisible, but 3630 3630, this by 66 was giving us 55. So this number is divisible, and after that, how many zeros you add, they all would be divisible. So if you have 63 shifted at least one place to the right, not immediately at the front, then it is divisible. So here we were having 363 and 2 zeros, so this would obviously be divisible, because at the end we were having 66 only. Okay, so basically for odd case, the last 5 digits, if you keep this, and then after that, whatever you have, fill those with 3333. Okay, so pairs of 3333, you can fill them up. That would be your pattern for odd case. Okay, so for n as odd, my pattern would be 333333, and at the end you would have 36366. Okay, so this would be my pattern for odd case, and for even case my pattern was this. And only thing that you need to handle separately is for n equal to 1 and n equal to 3, you would get a -1 case. After that, from n equal to 4, you would never get -1 case. From those pattern you can analyze. So finally what I would do, I would just check if n is 1 or 3, I would print -1. Otherwise, if n is even, then print this pattern, n minus 2 times 3 and 6 6. If n is odd, then print this pattern, So here we have last 4 digits are 6366, and here we have n minus 4 times 3. Okay, so this is what we need to do. So if you look at the code, if n is 1 or 3, print a -1. If n is even, n minus 2 times 3. Okay, this would print n minus 2 times 3 and then a 6. If n is odd, then n minus 4 times 3. Okay, this would print n minus 4 times 3 and then 6366. Okay, n minus 4 times 3 and then 6366. Okay, so this was like purely based on observation just by looking at test cases. Okay, if you were not able to observe, okay, this is one solution for this problem. Okay, by looking at test cases and by observation, if you find the patterns, this is the solution. Its time complexity would be like n times you are printing. So this would go to order of n. This would also go to order of n. So overall time complexity is, you can say, order of n you are able to find. And if you look at the constant, n was just 500 only. So something more than n was also okay for this question. So if you were not able to find the pattern, like what I did during the contest, I did not try to look too much at the pattern. I did it with a DP solution. So I'm not going too much into, but in short, I would explain what I did, because getting the pattern is something uh, like during the contest, for me it was more easy to apply a DP type of thing, just checking what I need to do, which is a more because looking at the constraints, you can apply something like n square or n into 66, something like that. So I used a DP of n into 66 to solve this problem. Okay, so this was one solution. This is an easier solution, I would say. I did not explain the DP solution because you would say for B problem I am using DP, so most of the people would not know DP. So that's why I explained you the easier solution. Now, for those interested in this DP solution, I would explain you in short this also. So what I did here is I just took a DP of 500 into 66, a DP of n cross 66. So where my DP state was, okay, in short, I'll explain this also. So if you are not able to get the pattern, this was a general way of solving this problem. So my n cross 66 DP I took, this state just represents if I want to form a size n, okay, DP of, I would say, n into j, that, okay, my DP state was DP n m for n into j only, let's say. If we want to find, if we want to form n digit number, okay, so we had to form an n digit number. So dpn is n digit number with uh, modulo 66 equal to j. Okay, so my final answer would be dpn0. Okay, so we need to find a number of n digit, modulo 66 is 0 basically, which is divisible by 66. Now to write the transitions, I needed to, like, for any digit I can place either a 3 or a 6. Now when I place a 3 at the ith digit, I am basically adding 3 into 10 to the power I minus 1 to my answer. So through this I was trying to calculate the transitions. So for that, my modulo j is going to below 66, I can calculate. This much is already done. Then 66 minus that would be required for the remaining. So I'm using a DP state of nj, where j is storing that I want to reach modulo 66 as j. So basically that's my DP state. So my transition would be very simple, that my DP ij would be either, if I'm going to DP n minus 1, so there case 1 is if I'm using a 3 here, case 2 is if I'm using a 6 here. So if I use a 3 and I can reach a DP of n minus 1, then I would use a 3 definitely. Otherwise, I will use a 6. So my DP state just returns whether I can form this or not. It just returns in 1 or 0. Okay, yes or no, whether this state is possible or not. I can form n digit number with modulo 66 equal to j. If we can form, it would return 1, otherwise a 0. So that's the DP state I stored, that if I use a 3 here, then the remaining I needed to find is j minus 3 into 10 to the power I modulo 66. Okay, this plus 66 mod 66 again we would do. Okay, so basically j minus this modulo 66 is what is now needed if j was needed here, and either this or, so if one of them is basically 0, I can if one of them is 1, overall would be 1 if in either of the case we can form. So here I would just use 6 into 10 to the power I modulo 66 plus 66 mod 66. Okay, so this was just my DP state, this or this. So this way I just found whether I can form a DP of size n with modulo 66 equal to j or not. After this, okay, so I'll show you what here I just pre-computed that for all the 500 values of n. Before the test cases only I pre-computed. So R3 is the remainder, j minus 3 into 10 to the power I minus 1 mod m plus m. M is 66 here. Okay, and R6 is if I'm using a path through 6, then this. So DP of this or this. Okay, now after this, in my code, what I would do, I would check if I can form n0 or not. If not, then I would print a -1. If yes, then one by one, I would check if using an R3 is okay. If DPI -1 R3 is okay, then I would set J as R3 and answer plus equal to 3. I would use a 3. Otherwise, I would use a 6. Okay, so I'll greedily just go on. If I can use a 3, I would use a 3 and print my answer. Okay, so I just explained you this. If you were able to get it, it's okay, no problem, because I did not found the pattern initially. I felt this more intuitive to solve. Okay, so I hope this problem is clear to everyone. If you didn't understand the DP solution, no problem. I hope you understood this basic solution, which I explained you using the pattern. Okay, so if this is problem is clear, we can move to the next problem now. Or if you have any doubt, just ask. Okay, I think we can move to the next problem now. So in problem C, what we are given is Alia has been given a hard problem. Unfortunately, she is too busy. Okay, so given an integer n, construct a permutation p of integers 1 to n that maximizes the value of k, which is initially 0, after the following process. Perform n operations on the ith operation. If I is odd, k equal to k and pi. If I is even, k equal to k or pi. Okay, so this is the operations you have to perform. Basically, what you need to do is, you are just given an integer n. You need to construct a permutation of size n so that when you perform an operation, you start with k equal to 0. Okay, so like you can see for the first test case, n was given as 5. The answer that is given here is this. So if you construct a permutation like this, what would happen? You start with k equal to 0. Okay. Okay, let's move it this side and explain you. Okay. So what you are given here is just a sec. So what you are given here is you are given like n. So n was given 5 as an input. So this was your output for this test case. Now, what you need to find is you are given an n, you need to construct a permutation. Okay, let's say this is the permutation that you constructed. For that, if you start with k equal to 0, the final k that you get by performing the operations, this should be maximized. Now, what is the k you get by performing operations in this case is you start with k equal to 0 for all the odd indexes. If I do the indexing, for all the odd indexes, you do a AND with pi for odd indexes. For all the even indexes, you do a OR with pi. Okay, so you start with k equal to 0, you do k and this was an odd index, so you do k equal to k and 2. Okay, so 0 and 2, it became 0 only. Now you went to I equal to 2. This was even, so you do a OR with Pi. So you do K equal to, it was 0. So 0 or 1. Sorry. So 0 or 1, it would become 1. Sorry, yeah. So after that, you would move to K equal to 3. So for odd, you would do a AND. So after that, your K was 1. So 1 and 3, you would do. So 1 and 3, that would be 1. Then you move to I equal to 4. Now, since this is even, you would do whatever K you had or with this value 4. Okay, so 1 or 4, in bitwise 1 is 1, 4 is this, so it would become 5. Okay, so you would get a 5. After that, you would move to 5. So K would become 5. And since this is odd, you would do a AND. So 5 and 5, it would be 5. So your final K after all the operations was 5. So with this, the final K you get after all the operations was 5. And this was the maximum that you could get. So this was your final answer. So you need to construct such a permutation so that the final K that you get is maximized. Okay. So for n equal to 5, okay, so for n equal to 5, the maximum K you can get was 5 using this permutation. That is what you need to output. For n equal to 6, the maximum you could get was 7 using this permutation. For n equal to 7, the maximum you could get was 7 using this permutation. Okay, so you can analyze the test cases like this. Okay, so how do we solve this problem? So first thing is observing the test cases only. Like for problem B also I showed you, just by observing the test cases you were able to find the pattern. So let's observe the sample test cases only, given test cases only. So for n equal to 5, my maximum K I would get was 5. Okay, so one observation you would get is, we are give whatever permutation we need to find, we need to form a n size permutation. Okay, now what all values you would do? You would do a AND with all the odd values. Okay, so all the odd indexes you would do an and for the even indexes you would do a OR. So you would start with an AND, then you would do a OR, then you would do a AND, then you would do a OR. Where you would end with, at the end, what you would do, if n was even. Okay, so if n was like, let's say, odd, then at the end you do a AND. Okay, the final thing you do was an AND operation. And if n was even, the final operation you do would be an OR operation. Okay, so one thing is for sure, whenever you do an AND, the numbers you have would be from the range 1 to n only. Okay, so the last number would be something in the range 1 to n. And whenever you do an AND, okay, so any number x, like any number x, if you have a number x, if you do a AND with a number y, the final answer is less than equal to x as well as y. Okay, whenever you do an AND of two numbers, the final resultant is going to be less than both the numbers. Okay, so if you do a your final operation is an AND operation, and if you're doing an AND with some number from the range 1 to n, okay, so your final K, for this case, I would say my final K is going to be less than equal to n only. It can never exceed n, because at last you are doing an AND operation with some number less than equal to n. So it can never exceed n. So the best you can get for odd case is n. Okay, now you can observe, for odd case n equal to 5, you got a 5. For n equal to 7, you got a 7. For n equal to 9, you got a 9. Okay, so by looking at this, the thing that you could guess is, for odd case, you are always able to make, if n is you are always able to make n. Okay, for sure you cannot make more than n, so n is the best you can make, so you would try to make n. So if you can make n would be the best that you can get. So you would try to make n for odd case. Okay, so by looking at the test case, it feels like for odd case, for n is equal to odd case, my final k is always going to be equal to n. This is the maximum that we can get. Okay, so now we will try ki how can we construct such a permutation so that we can get a n at the end always. Okay, so that we would try. Now let's look for even case also. Okay, for even case, what is happening? You know, the final operation is an OR operation. So at the end, we are doing an OR with some number pi. Okay, so for OR, you know, when you do an OR, that is always greater than equal to, if you do x or y, the resultant you get is greater than equal to x as well as greater than equal to y. So you know for sure, like if you keep a n at the end, at least n you can always make. Okay, so this final k is greater than equal to n, you know, like worst case, what you would do, you would keep a n at the end and you would get an n. So you can always make at least n, that is for sure. Okay, whatever permutation you take at the start, at the last, if you keep an n, your final answer would be greater than n. Now, what is the highest you can go? Let's look at the test cases for n equal to 6, even case. You were able to go up till 7. For n equal to 8, you were able to go up till 15. For n equal to 10, you were able to go up till 15. Now, can you notice something in this 7, 15, 15? Okay. These are the like these are the numbers with all the bits set. Okay, so 7 is this 111, 15 is this 1111 in binary. So this was my lower limit that for the final answer that I get. If you try to calculate the upper limit of what you can at max you can get. Okay, so you are always doing bitwise and bitwise OR operations. So if your final number is, let's say, like in one of the test case, your final number was n equal to 10. Okay. So 10 in bitwise is, I think, 1010. This is 10 in binary. Okay. Before that, you have all bits 00. And for n equal to 10, you would have numbers from 1 to 10. Okay. So 1 is 00001. Then 2 is 103 is 11, like that. Now, all these numbers at max they would have these first 4 bits they where there would be some value. After this, if 10, the highest set bit in 10 is this fourth bit, after that these bits would be unset for all the numbers less than 10, that you know for sure. So whenever you do an OR operation and operation, you can only set these bits. You can never set these bits by either doing and or. All the bits are 000. Whether you do and or, it would remain 0. So whatever operation you do at max, what you can get is set all these bits. So set all these bits, it's become 1111. Now know by looking at test cases also, you were able to see that for this my final answer was 151111. For n equal to 6, if you see, for n equal to 6, 6 is 110. Okay, so all remaining bits are set. Its highest set bit is this. So just set all the bits. This number is 7. So 7 was my maximum k that I could get. So this is, this is by this theory, you know this is the maximum you can get. So if you can make this number, that's the best thing. Like for odd case, by that theory, the maximum you can get is n. And from test cases, you were able to see that yes, you are getting n only. So I think there is a way to make n odd. We will try to find such a way. For even case, the maximum you can get is set all the bits. Okay, so whatever is the highest set bit in n, after that set all the bits also, that the number that you get, that if you can get to that, that is the best you can get. And from test cases, you can see always you are able to get. So if we can find a way to get this always, that would be the best answer. Okay, so these things by observation. Now let's try to find some permutation so that for odd case you can always get an n. For even case you can always get a number with all bits set. So how can you get that? So let's analyze separately. Okay. Now for odd and even, one more observation that I would tell, like for n equal to 6, your answer was 7. For n equal to 7, your answer was 7. Okay, so 7 was like you can say for even case, the last thing you do is on the nth number. Okay, whatever is at the nth number, you do an OR operation to that. Okay, now if you know that for even case till here you can always get a number with all the bits set, then at n plus 1, so I'm telling that n is even. Now if you want to calculate the answer for n plus 1, so n was 6 here, so for 6 if you can get a 7, and in n plus 1 you keep a 7, so 7 and 7 you would get a 7. So if for even case, if you are able to solve the problem that till n, for even n, if you are able to set all the bits, then from that, if you just do a and with n plus 1, it would result you n plus 1. Okay, so any number with all the bits set, in that if you do a like if this is your n plus 1, if you and with some n plus 1, the final answer you would get would be this n plus 1 only. Okay, the and with all set bits is not going to affect. Okay, and for like odd case, you needed to find this n plus 1 only. Okay, so for n equal to 7, your final answer should have been 7. So if you can solve the problem for even case, you can get all the bits set, then just add a n plus 1 to that. Your problem is solved for odd case also. I hope you understood a little bit. Now let's try to solve the problem for even case only. Okay, so what I told you is if n is odd, then what I would do is solve the problem for n minus 1. N minus 1 was an even number. Whatever permutation you get, to that just append n. Okay, so n minus 1 would have a permutation from 1 to n minus 1. In that, if you just append n, that would be your answer for odd case. Okay, so for even case, you just need to write this solve function, just solve this problem for even case. For odd case, just whatever was the solution for n minus 1, which was even, through above, just add a n to that. Okay. Append an n to the end of that. That would be the answer for odd case. I hope you understood this thing. Now let's try to solve this problem for even case only. Now let's look at the observe for n equal to 6. This was my basically answer. Okay, like let's try to make it like for any n, let's say n is 10. Okay, what you need to get is 15 as your final answer with all the bits set. So how can you get that till 10? So if you look 7 you have 111, then 8 you have 1000. Okay, so and then 9, 10 are some numbers. In 6 you have this 5 is this. Okay, so what you need is finally you need 15, which is 1111. Okay, so if you want to make 15 using numbers from 1 to 10 only. Okay, so first thing is you can utilize this 7 where you would be able to set all these 3 bits, and you can utilize this 8 where you will be able to set this bit. So first thing, like uh, you are assuming that for even case you are always able to solve the problem. So you have an 8 through which you can set this bit. Now, if you can solve the problem for till 7, if you can, whatever is your solution, you can obtain all these 111. Okay. Then to that, if you do an OR with 8, you would get 1111. So that's the end thing you would do is at the end, you need to get 15. So whatever permutation you have, at the end, you would have an 8 so that you through 8, like it is even. So this would be a So at the 10th place, you are at the nth place, you are going to have an 8. So you would do an OR with 8 and your series would end. Before that, if you can make a 7 before that, then 7 or 8 is going to give you 15. Okay. So if you can somehow make a 7 till here, this thing, then or 8 would give you 15. So how can you make a 7 here is, like whatever is your answer for 6, your solution, whatever would be your solution for 6, in that if you add a 7, here you are doing an and with 7. Okay, so here you would definitely keep a 7, and before that you would try to make till here a 7 till here. Okay, using 1 to 6, you can make a 7. So how would you do that is, um you are doing, if you use a 6 here. Okay, so with 6 you are doing an or with 6. Okay, here you have an or and like this it is going. So till here you want to make 7. So with and you need to add a 7, and then you do add with 7. If you take any number less than 7, you won't be able to make 7. So here definitely you would have to have a 7 with and with 6 here, if you do an or with 6, whatever number is before, you would get at least 6 here. So you have set these two bits, and with 7, it means these two bits would be set. Only thing you need to make sure is how would you set this bit. So before that, you need to set the ones bit. So any odd number would have the ones bit set. So what I'm doing is using a 1 and 3 here. So and with 3 is going to make sure that this one bit is set, and or with 1 is going to make sure this bit is set. Okay, so before that we can have any numbers. So what I'm telling is, just have any numbers. From here, if you see any number or with 1, here this thing is at least going to be equal to 1 when you do an or with 1. After that, when you do an and with 3, okay, this one's place is set in 3 also, 1 also. So here again, at least 1 is going to stay. Okay, this one's place is not going to get unset when you do like any number greater than equal to 1, like with one's bit is set. Okay, any number whose one's bit is set, this is any number whose one's bit is set. If you do an and with 3, okay, so if you do an and with 3, this number is also going to have the ones bit set. Okay, so after this also, your ones bit is going to be set. After that, you do an or with 6. Okay, so after that, if you do an or with 6, that means you are going to get at least 7 here. Okay, so this 6 had all the bits set except the ones bit, which is going to get set by this when you do an or operation. So after this, like after doing the or, you are going to get 7 at least, and 7 and 7 is going to give you 7. So whatever numbers you have here doesn't matter. If you perform this sequence of operation, you would get a 7. After that, you perform with 8, you would get finally 15. So after that, you are going to get 15. Sorry, I got disconnected. I'm audible now. Okay, I think I'm screen is also visible now, right? Okay, so what I was explaining is uh if you have these five numbers at the end, then any numbers you have here, it doesn't matter. Finally, you would get 15. Okay, as I explained, any number you have here, if you do an OR with one, you would have at least the ones place set. Anything here, then a ones place set. After that, if you do an AND with three, again, your ones place is going to be set for sure, add because three also has ones place set. After that if you do an OR with six, okay, so these one and three we were using to make sure my ones place is set. Okay, so these are used to make sure ones place is set, or like zeroth bit, I would say, to make sure the zeroth bit is set. Okay, so we use 1 and 3 to make the 0th bit set. After that, we use a 6 to set all the bits, basically, because 6 had all the bits set except 1, except the 0th bit. So we use 1 and 3 for the 0th bit, and then we use a 6. So or with these two or with 6 is going to make sure that I get a 7 here. And then 7 and is going to make sure that after this also I keep a 7. And then 7 and 8 is going to make sure I get a 15. Okay. So this was the approach for whatever even n equal to 8. For that also I can get a 15, n equal to 10. For that so I can get a 15, n equal to 12, n equal to 14. For these numbers, their most significant bit is the fourth bit. Okay, this is the for all the numbers whose most significant bit is this, you can get 15 here. Okay, now if you move ahead, if you move to n equal to 16, it would have this fifth bit set. So for that, you can make 31. Okay, so all these bit set would be 31. So basically what you can do is take the log of n to check how many, what is the most significant bit which is set in binary. So and then just set all the bits, the number that it's making, this is what you want to get. Okay, so if you want to get 15, what you do is the last numbers you get is 876. If you use these numbers and a 3 1, then you get finally. So if you want to basically make any number which is 2 to the power, okay, whatever number you want to, like, for even case, what I'm telling is you would compute like x equal to log base 2n. This is going to give you the how many bits are set in this like most significant bit which is set. So if you do 2 to the power x, okay, so if my n was 10, my x would be the log of this in integer, it would be 3. So 2 to the power 3 is going to give me 8, like in this 2 to the power x is going to give me 8. So basically what I'm trying to make is 2 to the power x plus 1 minus 1. Okay, so 2 to the power 4 minus 1 is 15. Okay, this is what I'm trying to make. Okay, and to make this, I would use 2 to the power x, which is 8. Then 2 to the power x minus 1. So this was 8, this was 7. Then 2 to the power x minus 2, this was 6. And then a 3 and a 1. And before that, I can use anything. So what I would do for any n, I would take log base 2n to find the number of bits which is set, the highest set bit. So the final answer, the final k that I am trying to make is 2 to the power x plus 1 minus 1. Okay. So for n equal to 10, this 2 to the power x plus 1 minus 1 is going to give me 15. Okay. So for any, for n equal to 16, x would be 4. So 2 to the power 5 minus 1 is 31. So 31 is what we are trying to make. I hope you got this is what we are trying to make. To make this, we would use at the end, we have to use 2 to the power x, 2 to the power x minus 1, 2 to the power x minus 2. These three would be used to finally make 2 to the power x plus 1 minus 1. And before that, 1 and 3 to set the ones bit. And before that, just put all the numbers in any order. Okay. So this is what is going to be my algorithm to solve the problem for even n. And for odd n, what I would do, I would use the same solution for if n is odd. I would use the same solution for n minus 1, which was even, this using this above case. And to that, I would append n. That would make my solution for n odd. And in odd case, my final k is going to be equal to n. I hope you understood a little bit. Uh, b- okay, so I think we can move to the code. If you have any doubts in this logic, you can ask. Basically, we had to maximize the number, so you have to look at the problem a little bit in bitwise to understand. Okay, so I hope this thing is clear to you. Like we had to set all the bits, which is what we had to make 15. So to make 15, I'm using an 8 which has this bit set, because till 7 I knew I can make, if I can make any 15, then I can make 7 also. So I assumed that I can make a 7, and then I use an 8 to make a 15. Okay. So my end value was 8, and then I would try how can I make a 7. So 7 was odd. So for odd case, we knew at the end I would have to have 7. Now before that, how can I make 6? So whenever it is 6 is just the 0th bit is unset. So an OR with 6, before that I have to make sure I have one set. So for that I use 1 and 3. Okay, so I hope you understood. Using 1, 3, 6, I'm able to make 7. And with 7, I'm able to make 7. Or with 8, I'm able to make 15. Same way, I can use it for any general case, that if I want to make 2 to the power x plus 1, I would use a 2 to the power x at the end. Before that, 2 to the power x minus 1. Before that, 2 to the power x minus 2. And 1 and 3. 1 and 3 is going to set my 0th bit. 2 to the power x minus 2 is going to, this overall is going to make 2 to the power x minus 1. And with 2 to the power x minus 1 is going to maintain 2 to the power x minus 1. Or with 2 to the power x is going to make 2 to the power x plus 1 minus 1. I hope it is clear. Yeah, as you told, if the sample test case were not given, the problem would have been a little harder. But with the sample cases, it made almost clear that what's my final K that I can make. Okay, once I knew that I can make this as the final K, I had to just figure out a way to make this. Okay, so, okay, now let's jump to the code. I hope you understood the logic. So now what I did here is I created this function to solve my answer for any even n. Okay, this function is going to return my permutation for any even n. Now, if my n was odd, what I did, I called this function for n minus 1. And in that answer, I pushed back n. So that's what my final answer becomes. Okay, so this is vector of int. Okay, so this answer, this function returns a vector containing the permutation till n minus 1. In that, I pushed back, this is pushed back, I pushed back n to get my final answer. So my maximum k for odd case is n, and my final answer is in this vector. I printed both of them. Or like I'm doing a direct C out, but this is overloaded in above. So it's actually, I'm printing all the values from my array. Okay. Like I have overloaded that in my template. So whenever you can write it like this, it would be better. Just run a for loop and print all the, you can write it for auto I to answer. Just see out I. Okay, this is what the code. If you didn't understand how I directly wrote see out answer, it's actually this. Okay. So you print n and then all the values from your array. And then, okay. This is also the same. Okay, now let's move to the function. What function? For even case, my answer was directly the function. Maximum k I can get was 2 to the power x plus 1 minus 1. Okay. So as I wrote here, maximum k I can get was 2 to the power x plus 1 minus 1, where x was log base 2 n. Okay, so I computed this log base 2 n. Okay, so this is x. So 1 left shift, x plus 1 is 2 to the power x plus 1 and k minus minus. So overall, I get 2 to the power x plus 1 minus 1. This is the k I print for even case, and then answer I computed from the function. I print all the values from my answer. Now let's see how I computed my answer. So what I told you, what I have to write is my last value is 2 to the power x. Before that, 2 to the power x minus 1, 2 to the power x minus 2. So in my array, I am just pushing back from the last. So this as the first, second, third, and then I would just reverse it. Okay. So what I did is, okay, for small n equal to 4 and 6 case, like this was not valid, because if you look for n equal to 6, my x that I get would be 2, which is log base 2 of 6 is 2. So 2 to the power x is would be 4, this would be 3, this would be 2, and then again 3 and 1 would be used. So this would be a little wrong. So from n equal to 8, this is valid. For smaller n equal to 4 and n equal to 6, I just copied the answer from the test case, given test case only. So for n equal to 6, like 4 was not there, n was at least 5. So only for n equal to 6, what I did is for n equal to 6, I copied this answer. Okay. Directly for n equal to 6, my answer is 124653, which is this 124653. And for n equal to 4 also I've written, because when n is 5, I would call n minus 1. Okay, when n is 5, I would call n minus 1, which is 4. So for that, this answer I wrote 2134. Okay, so 2134. So these two cases I handle just separately only. After that, I just wrote my general case, which is x is log base to n. I got x, y is 2 to the power x. So I have to just push back 2 to the power x minus 1 minus 2. So I push back y as 2 to the power x, push back y minus 1, y minus 2. Then 3, then 1. Okay. After that, I push back 3 and 1. After that, just push all the elements in any order. It doesn't matter. So I just followed any order. I already have pushed 3 and 1. So 2 is remaining. So after that, I just pushed a 2. So 2 is pushed. After that, from 4 up till y minus 2, up till less than y minus 2. So from 4 till less than this, all those values I pushed, those were remaining. Then y minus 2 to y I have already pushed. So y plus 1 till n, those values I pushed. Okay, so these can be done in any order. Okay, till here you had to follow this order only. After that, just any order, and then I reversed it. Okay, so because this would be at the end, not the first, so I reversed it and returned my answer. So this was just the way to implement. You can write it in any way. Okay, this was how I implemented. Okay, I hope you understood the logic behind this function and the whole code. If there is any doubt, you can ask. So the time complexity would be for the function I'm calling for n. So these are direct return. After that, whatever this x is, I am just pushing back. uh, I'm using the pushback at max n times. I'm pushing n values to my answer array. So this function is overall order of n. Okay. And only this function order of n function is called. This is order of one operations, order of n function, order of one operations. Okay. This printing is order of n. So overall thing here is order of n only. So in order of n, we are finding space complexity would also be order of n. We are using an array of size n. That's what we are using at max. And the constraints was n was given as 2 into 10 power 5. So this is well accepted. I hope this problem is clear to you. If you have any doubts, you can ask, or we'll move to the next problem now. Okay, so let's move to the next problem. So problem D we have, you are given an array B of length M. You can perform the following operation any number of times, possibly 0. Choose two distinct indices I and J, where I and J are from the range 1 to M and Bi is even. Divide Bi by 2 and multiply Bj by 2. Your task is to maximize the sum of the array after performing any number of such operations. Since it could be large, output this sum modulo 1 in n plus 7. Since this problem is too easy, you are given an array of length n and need to solve the problem from each prefix of A. So for every prefix of A, you need to find this thing. You need to find the maximum sum of the array you can get if you can perform this operation any number of times. What is this operation? Just select any index I such that I is less than j and bi is even. So just divide bi by 2, multiply bj by 2. This is the operation you can do, is divide an index at index I, divide the value by 2 and multiply some other value at a forward index by 2. Perform this operation as many times and finally maximize that sum of the array and find this answer for every prefix of A. Okay, so if you look at the first test case, this was the array given to us. Now, first we need to find the answer for the first prefix for this array. For this array, only one index is there. You can't perform any operations. Sum is 1. It would remain 1. For 1 and 2, like you can perform an operation if you choose this as I, this as j, but this is not even. You cannot divide it by 2. So you can't perform any operation here. So it would remain this only. Sum is 3. Okay, now for after that, for the third prefix, which is 1, 2, 3, again, for this, you can divide this second by 2 and multiply this by 2. Okay, so for this third prefix, what we did is, for this prefix, we divided this 2 by 2, it became 1, and multiplied this 3 by 2, it became 6. Okay, so it became 116, whose sum was 8. Before that, before doing the operation, we had 1 plus 2 plus 3, sum was 6. So by doing this operation, we reached the sum 8. So 8 is the maximum you can get in this case. Okay, so for the next case, which is for this prefix from 1 to 4, what you did is divided this by 2, made it 1, and multiplied this 4 by 2, made it 8. So it became 1138. Okay, so sum was 30. Okay, likewise, you can see this is going. Okay, after that, you multiplied the next value 5. All the twos from here and here, they were multiplied there and it became 40. Sum became 46. Okay, so again, here you can look at the test case, these sample cases and understand something. But okay, let's understand this problem, what you can do here. Okay, I hope you understood the problem, what you need to do. For every prefix, you need to find this final answers, okay, for every prefix. Now, this n is in 2 into 10 power 5. You cannot do something like n square here. So for every prefix, if you are separately calculating in order of n, that won't be accepted, you know. For every prefix, if you're separately calculating in order of n, that would go order of n square. So that won't be accepted. Now, what you can do here is, let's see. Okay, so you have some array. In this, what you can do is, okay, let's say for any prefix, if you want to, if you are computing separately also, if you can compute in order of n, then we would look how can we update that. If separately also, for any array you want to compute. Okay, let's take this array. 1, 2, 3, 4, 5. What is the maximum you can get by the operations that you can perform? What are the operations? Is you select some value which is even, divide it by 2, and multiply some other value by 2. Okay, let's say you multiply this by 2, made it 10. So your operation, one of possible operation made it half, made it double. Okay, it became this. After that, again, you can perform the operation now. These are odd values. You cannot apply operations here. This is even. You can divide it by 2, make this double. Okay, it became this. Again, here, this is an even value. You can divide it by 2, make this double. Okay, it became this. Okay, so here, after this, you cannot perform any operation. This is an even value, but it doesn't have anything in the forward where you can transfer its factor of 2. So here the maximum sum was this 1 plus 1 plus 3 plus 1 plus 20, which was 26 in this case. Now, how can you maximize this? If you think, what is the operation that we are performing? For any number, till when can you divide a number by 2? If a number is x, how many times can you divide it by 2? Is number of times it is having 2 in its factorization. So if this x is 2 to the power I into something y, where this y is an odd number, it doesn't have 2 in its 2 as its factor. So number of factors of 2 that x has, this is the, if it has I number of factors of 2, these are the number of times you can divide this x. Okay, and this I would go at max log of x times. Okay, that won't be too much. So you can just directly calculate it for every basically value, for every index. You can just write every value in the form of 2 to the power I into y. Okay, so what I'm doing is, first thing, I can break down every value in this form. Number of factors of 2 that I have. Okay, and after removing those factors of 2, what is the odd y that I get? Now this is the minimum you can reduce that a value to. And these I multiples of 2 that you have, they can be transferred ahead. Okay, or instead of writing I is denoted as an index, so better I would write x here and ai here. Okay, so this would be a more better way to represent. So for any I would transform it in this form, 2 to the power x into y, where x is the number of factors of number of powers of 2 that this ai has, and y is the number after removing all those powers of 2. Okay, this you can easily compute is divide ai by 2 continuously. Keep on dividing until ai becomes odd. So the final ai that it becomes, that's your y, and number of times you divided, that you can count and store it as your x. Okay, so first just store the every number in this form. Now, once you have this form, what you can do is you can transfer these x ahead. Okay, so for every index I, if you have a number in this form, this would always remain. So this is some property of that index only, that this value is going to remain there for sure. But this x, this is movable. This can be moved ahead. Okay, that's it. That is the thing. If you just remove one power of 2, x would become -1, and to some other index, his power of x would become would increase by 1. So these x powers are movable. Now, where would you want to move these powers to so that your final answer is maximized? Okay, if you look at two numbers, okay, at some index I, you have 2 to the power x1 into y1. At some index j, you have 2 to the power x2 into y2. Okay, so what would be the best to keep these x1 powers? Would you keep it with y1 or would you keep it with y2? So you would look where you would have more value. There you would keep it. So if you are multiplying 2 to the power x with y1, or if you are multiplying 2 to the power x1 with this value, okay, now this x2 is not movable to the left. It can only move to the right. Okay, so you cannot transfer these x2 here, but you can transfer this x1 here. So the thing is, would you transfer this x1 here? Is if this value, so if you transfer it here, it would now its sum is 2 to the power x1 into y1 plus 2 to the power x2 into y2. This is the current sum. You can say this is the current sum. And if you move it here, my new sum would be y1 would remain y1, and these powers are moved, it would become 2 to the power x1 plus x2 times y2. Now, which is more? This is more or this is more? How would you compare that? Is if you just try to compare them, then this 2 to the power x1 is multiplied with y1 here, and it 2 to the power x1 is multiplied with this here. So among this and this, whichever is greater, multiplying that with 2 to the power something is going to make it more greater. So we can say that we would move here, this would be greater only if, okay, like mathematically also you can find, you can write it like this. Okay, you want new sum to be greater, so you want this to be greater. So if you write it like this, if you move y1 there, then 2 to the power x1 minus 1 times y1 less than 2 to the power x2 y2, if you take in common, then 2 to the power x1 minus 1. Okay, so these are common things you can cut. So basically, if y1 is less than 2 to the power x2 y2, then you would move it there. Or from that also you can understand, if this value was greater, then you would move it here, because it would be better that these powers are with some greater value. That's the result that you get, that if this value is greater, you would move it there. Okay, so basically, if the next value, that if there is some value ahead, okay, the overall value, if this is greater than the base value, then you would move these powers ahead. That's your condition for moving it ahead. Okay, so if you understand this, then I think it would be a little bit more clear what we are doing is, in general, what we would have some array. Okay, we would have 2 to the power x1 y1, 2 to the power x2 y2, 2 to the power x3 y3, like that. Okay, so how would you proceed? Okay, first every value divided it in this form, 2 to the power something into y. Now you you have to calculate your answer for every prefix. Okay, so how would you move? First, for this prefix, this value would only be your answer. Okay, here you cannot perform any operation. So for the first case, here you would have this only as answer. Just store that in your answer array. Now, when you move ahead, when you move here, now you can transfer these values here. Whether you would transfer, that would depend. If this y1 is less than this whole thing, then you would transfer this ahead. Once you transfer this ahead, you would update your answer. So initially your answer was this. Okay. So initially in your answer, you had 2 to the power x1 y1. When you moved here, you need to update your answer. So if you are moving it, if you are not moving it, just add this to your answer. If you are moving it, then how would you update your answer is, let's say you are moving this x1 here. So before you had 2 to the power x1 added, so what you would do from the answer, you would subtract this 2 to the power x1 times y1. This is not there, but only y1 is there. Okay. So basically what you are doing is subtract this value and add this value. This you can just update. If you are moving it here, then before you had this in your answer, so subtracted that and you added y1. Now you only have only y1 there, and you add this to your answer also. Okay, 2 to the power x1 plus x2 times y2. Okay, so this way you can update your answer. Same way when you move here, now you would check that before that, whatever you had. Okay, if this y2 is less than this whole thing, you would move these powers here. Now, what if it was not less? Okay, like would it go just directly just checking with the last value would be okay? No, it may happen something like that. Okay, here I told that you moved it. Let's say you were not able to move it. Let's say here the case was that 2 to the power x2 y2. this was less than y1. Okay, so y1 was greater than this. Like from the test case, you can understand that here you had something like, let's say, this was 2 to the power 3 into 6 or into 7 you had. After that, you have, let's say you have a 6 here, which is 2 to the power 1 into 3. Okay. So if you have a 6 here, after that, then you would compare this value with this value. 6 is less than 7. So you would not move it here. You would keep 2 to the power 3 here only. Okay. So after that next value that you move to, let's say this is 3. Okay. 2 to the power 0 into 3. This is the third value. Okay. Let's say this is the next value. Then what you would do is you have some powers here, you have some powers here. For this, you can either move these powers here, you can also move these powers here. Okay, so you would have to check with both of them. Now, it may happen some powers would be here, here, here. So if you're checking, going back and traversing to every index and checking with every value, again, that would take order of n. So overall, it would become order of n square. That you cannot do. But actually, if you look before that, how many values would be there that would keep a power? If you analyze it more carefully, is, let's say you have this case. Now what happens? You have a 3 here. 3 would be compared with this 3. Okay, so if this is equal case, like you can move it or not move it, both would be okay. No, like if you have a 3 here, that would be compared with 3. Okay, you can move it or not move it. Let's say you have a 6 here. Okay. Okay, so it was like this. This 8 into 7, 56, then 6, then 6. Okay, this was your test case, let's say. 56, then 6, then 6. Okay, so you reduced 56 into this. After that, you have a 6, you have a 6. Now, this 6 you compared with 7, you cannot transfer, so you did not transfer. Now you move to here. With this 6, you compared with this. Okay, so this 6 got compared with this 3, it was greater, so you can transfer. So what you did is you transferred this here and made it a plus 1. So basically this became 3, this became 12. Okay, this is what you effectively did. After this, you can also transfer this here. So you would check with this. Now, once you have transferred this one power, it became 12 now. So 12 can be compared with 7, not 6, because it already has become 12. So adding this 2 to the power 3 to 12 would be beneficial than keeping it with 7. So you would compare 12 with 7, then you can see that you can transfer this power. So this power would also get transferred now, and a plus 3 would get added to this power also. So but what if okay, this was one case, you travel back and you transferred all the powers. Now at max, how many times would you travel back? Okay, basically what would happen if you have some source where there are some powers of 2. Okay, so if you have this array, there would be some points here, there is some powers of 2 remaining. After that, there is some value where it didn't got transferred. Okay, so here also again some powers of 2 is remaining, again some powers of 2 is remaining. How many steps would be there? Okay, so if you look at some place, at some index, this is some index I where some power of 2 is left. This is some index, let's say I2, where some power of 2 is left. This is some index I3 where some power of 2 is left. Okay, at max, how many such indexes can exist at a time? If these both are existing, it means you were not able to transfer this power here. It means whatever its like y value is, y of I2, whatever is, and the power that it has. Okay, so like 2 to the power x, whatever that is, this 2 to the power x times y was less than this y, whatever y was here. Okay, it means, and this has some power. This x is greater than equal to 1. Okay, we are not considering those index where x is 0, 2 to the power 0. it doesn't contain any power, it cannot transfer, so we would ignore those. So we would only store those indexes which has some power of 2 left in it. So if it has some power of 2 left in it, it means at least it is 1. So at minimum, you are telling that y of I1, okay, let's say this is y1, this is y2, some other two. Okay. More correct would be to write I1 and I2, but I'm writing it y1 and y2 only. Okay. It's 2 to the power x1 into y1. Okay. So if these two are existing together, it means that 2 to the power x2 into y2, this was less than y1, then only. Same way, this is existing, it means 2 to the power x3, y3. It means 2 to the power x3, y3, this was less than y2 alone. Okay, these conditions are satisfied, then only they are existing. Otherwise, all the powers would be transferred here. It would have x1 as 0, so we would not consider it. We are only keeping track of those positions where some power of 2 is stored there, which can be transferred ahead. Okay, so but it is not transferred. So if it is not transferred, it means this y1 is greater than this. If this is not transferred, it means this y2 is greater than this whole thing. Okay, so if we look, this x2 is at least greater than equal to 1. It means at minimum, if you write this y1 is at least greater than 2 times y2, that I can say, or more also. It can be more, but at least it is more than 2 times y2. And this here also we can say this y2 is at least 2 times more than y3. So when we are moving here, we are at least moving into 2 into 2 into 2. So, and go, this y can go less than equal to 10 to the power 9. You can look at the constraints of the problem. AI is up to 10 to the power 9, so y would obviously be less than equal to that only. So if you have 10 to the power 9 and you have these steps, okay, where some powers are stored, okay, and all these steps, whenever you move here, you are at least going into 2. Whenever you are move here, at least into 2 you are going. So at max you would have how many? After like 2 to the power 30 crosses 10 to the power 9. So at max 30 places would be there where some powers are stored, not more than that. So it would be, so if you just go to all the previous places where some power is there and check, that would take order of 30 time only. So in n into 30 time overall, you can solve the problem. It won't go n square. That is the thing to observe. Okay. So it would look that you are going order of n square if you are going backtracking to all those positions where some powers of 2 is stored. But if you look at if you look closely, then whenever you are going back and that is not transferred here, it means it is at least 2 times that. So if you are going 2 times, 2 times, 2 times, at max you would go 30 times, not more than that. Okay. So otherwise it would get transformed. It is not more than 2 times. Okay. So one of them would, if it gets transferred, it is finished. Okay. So to implement that, what we would do, whenever we have some position where some two powers of 2 is left, we would push them into a stack. Okay. And whenever you are visiting an index I, from the end, we would check if we can transfer this here, transfer here. If you can transfer this here, transfer here. Okay, whenever we cannot transfer, now the ahead values would be even bigger. So you don't need to check there. Okay, so you would always check from here. Just transfer all the values which you can. After that, if you cannot transfer, just stop there and break there. Okay, so you would just pop these from your stack, and whatever you get there, that would be pushed into the stack. So like the size of the stack would at max go 30. Okay, in the stack, you would store x1, y1, the power of 2 and the base value. Okay, likewise, we would keep updating. So I'll show you the code. With that, you would understand a little better what I'm doing. Okay, with the code only, I'll explain you. So what I did is this was the input. Okay, I just took the input. After that, I initialize the stack. This is pair of long. Okay, so this stack would store a pair of x comma y, basically the power of 2 that we have and the value that we have. That is what I'm going to store in the stack. Okay, so after that, I have this answer vector initialized. So I would start with I equal to 1, go up till n. Now, first thing I would do in AI, from AI, I would extract x and y. How would I do that? Till the time this AI is divisible by 2, I would divide it by 2 and do C++. So in C, I would have the powers of 2 that it has. So now I have that this current AI, AI denotes my Y. So now if I want to write is my Y is basically AI. Okay, AI is only reduced to Y and my X is C. Okay, that I explained you in the solution. I have reduced my AI into 2 to the power 2 to the power X into Y. Okay, so it is 2 to the power C into AI only effectively. Okay, so AI only reduced to Y and C is the powers in my code. Okay, C is X in my code. So this is what I did to find the number of powers that is has. I reduced it in the form of 2 to the power X into Y. After that, my answer. So for any index, first I would assume that till I minus 1, whatever answer I calculated, that is my answer. In that, I would update my answer after transferring the powers. So here I am transferring the powers. Okay, so while the stack is empty, I would try. Okay, what I'm doing here is whenever I'm moving here, okay, I would check this. Whatever, if it has some powers of 2 stored in it, I would push it into a stack. After that, when I went to this, I would check from the top of the stack. I would check from the top of the stack whether I can transfer these powers here. If yes, then pop this stack, transfer these powers here. Again, I would keep on checking in the stack until it's empty, or if I cannot transfer till there, I would check and transfer those powers here and then push this into a stack. So when I'm moving here, I would in the stack, I would have all those places where I have at least some power of 2 stored. Okay. So whenever I'm moving here, so I would just check till the time. So one more thing is, in order to compare, what we were comparing is y1 greater than 2 to the power x2 into y2. Now, when these powers are pushed ahead, this x2 can go to some really large number. So 2 to the power x2 can even exceed our 10 to the power 18 limit. Okay. So I'm not calculating 2 to the power x2 uh, directly. If my x2 is greater than 30, then I know this is going past 1e9. So it would obviously be greater than y1. So if it is greater than like 32, if it has my C, the current power has reached greater than 32, I know it's definitely greater than y1. So that is okay, because if I write this AI into 2 to the power C, this may exceed my long range. So just to avoid that, I have handled this separately. If my C is going par 32, I'm not doing it 2 to the power C. If I do 2 to the power C, then it may exceed long range. So I'm directly writing an OR condition. It would become true. Or if my stack dot top dot first, so stack the top of the stack, the first dot first, I'm storing y1. So in the top of the stack, okay, whatever was there, let's say this was there in the top of the stack, 2 to the power 3 into 7. So 7 is stored in dot first and 3 is stored in dot second. Okay, this is the way I'm storing it. So I would I have to check this y1 whether this is less than this whole value 2 to the power x into current y. So whether this stack dot top dot first, the last y1 where some powers of 2 exist, if this is less than ai into 2 to the power c, the current value, then we would have to push the powers into ai. So what we would do, we would take the value, dot first is the value, which is y, and p is the power dot second, which is x, as I explained. Okay, so in ai, what I would in c, I would add p. Okay, so these powers, okay, so these powers are moved here. So this powers is denoted by p here. In stack dot second, I have stored p. So this p power is now added to here. Okay, so this c plus equal to p I'm doing. So in c, I'm storing the current power. So in that, I'm adding p. Okay, and how I'm updating my answer? In answer, I would subtract val into 2 to the power p. Okay, so previously this was storing 2 to the power 3 into 7. So as I told, I would subtract 2 to the power x into y. So 2 to the power p into val. Okay, so val is y, p is x. So this is subtracted. Okay, and I would obviously do mod m. Final answer is mod m. So I'm doing a mod m everywhere. Power m is doing 2 to the power p in mod m form. Okay, this is a binary exponentiation function which is calculating x to the power n mod m. Okay, it's doing mod m always. So that it doesn't exceed the long range. I'm doing it everywhere mod m. So val into 2 to the power p mod m. Okay, since I'm doing subtracting, so I have to do a plus m mod m. In mod m, you know the property of modulo. Whenever you do subtraction, you have to do a plus m to maintain it mod m. So this is the thing that I am subtracting, and what I'm adding is y1. Okay, so answer plus val is getting added. So this thing is, this power has been removed here. This updation is done. This I would add finally after all the powers are moved here. Whatever the I get, that would be like finally added to my answer after the while loop. Okay. If this condition is not satisfied, I would just break. I would not check further. After that, in the stack, I would push AI and C. Okay, you can see the value is pushed in dot first. Okay, the Y, and the power is pushed in dot second. Okay, and AI is updated as AI into 2 to the power C. Okay, this thing. Okay, 2 to the power C that I get into AI. Like answer I is updated as AI into 2 to the power C. So this is how my answer got updated after doing this thing. Okay, and then finally I'm just printing my answer. I hope this is clear to you. If you have any doubts in this, you can ask those who are watching till now, or I hope it is clear. If not, okay, basically, it was a little bit tricky to understand, but the thing was you had to look at the powers of two. Okay, so the powers of two were getting transferred, and you had to store them in a optimal way. Okay, so yeah, maybe you can rewatch it one more time if it's taking some time to digest, and just look at the code one more time, analyze it yourself once, then you would understand it. So if you look at the time complexity of this code, this was input part order of n. I've initialized the stack, and then this while loop at max, I would divide by 2, divide by 2. This would go, this while loop would go at max log of AI times. Okay. This is the maximum log of AI times this while loop would run. After that, this while loop, overall, as I explained there in the proof, that this stack would at max have a size of log of AI, which is about 30. So this would also run at max log of AI times only, which is what I explained here, the proof that it would go at least two times. Okay, it would be at least into two times. So at max, it would have log base 2 of AI times only, these much step only, at max 30 steps only. So this while loop would also run at max log of AI times only. Okay, this stack and all is done. This is order of 1, and inside that, here I'm using a power function. So this would take a log n time to do the binary exponentiation. Okay, so this is taking log n for binary exponentiation. So overall, I should write it log of AI into log of n. Okay, so for this, and this is push, this is log of n for the binary exponentiation. Overall, this is done n times. So this become order of n into log n into log of AI. Okay, so okay, this would be the overall time complexity basically. Then we are just printing it. Okay, so my overall time complexity is order of n into log n into log of ai. So log of ai is 30, log of n is like 20. So 20 into 30 into 1e5. Okay, 2e5. That would be accepted. That would be around 1e7 overall. Okay, so this is accepted, this time complexity. And my space complexity is going to be, I think, an stack would store at max 30 size and an n sized array, n sized answer. So order of n only. Okay, I hope this problem is clear to you. Yeah, it took me also a lot of time. Initially, I had understood the like one logic a little wrong. Like I explained to you that you had to add these powers. This was the comparison, but I was comparing y1 greater than y2 only. But actually, you had to compare this. So I was doing this. So I had implemented that, but that went wrong. Then I realized that you have to compare like this. So then I implemented this. So yeah, it took a lot of time to implement. This was a little tough problem, I would say. Okay. So I hope you understood the problem, or maybe just watch it one more time. You would understand. So thank you so much for tuning in. Goodbye.